Orbit, a unique perspective on the planet. The permanently manned International Space Station circles overhead. It too gives us a unique perspective on science, health, and industry. The benefits of manufacturing in zero-G is spurring other countries and private companies to join this elite club of manned space stations. Low-cost, reusable manned spacecraft is the key to industrial expansion into space. SpaceX, with its Dragon spacecraft and Falcon rocket combination, is fulfilling that need. And other companies will follow.
It will become possible for people, I mean, of course, when I see all this, I've just yesterday seen the Dragon capsule right in front of me. We were able to get closer up to the same level. And I have to say, this is so fascinating. I really would like to step in and sit down and take off. It is a dream for many people.
This is what Dragon is.
Currently, the ISS is the only destination.
Space station and the forward.
The station is 23 years old and is reaching the limits of its ability to service other industrial needs. However, it is imperative to keep the research and science going.
Because we do so much work on the space station, research, experiments that really help humanity, but also give us a different view of our planet. And at the end, we want to protect our planet, and our astronauts are really giving us messages back, which is quite unique and quite nice.
When we look at the science that's done on the space station, it's benefited us on Earth in a lot of different ways. And I think one is a very basic way, in that it's given the opportunity to scientists throughout the world to think about science in a different way. When we think about life as we know it, one fundamental property of all life has been gravity. And one of the first things scientists do is they think, what happens if we take gravity away? And on the International Space Station, we're allowed to do experiments that study just that for long periods of time. So we can study the effect of gravity on things, on people, and then sometimes we can combine that with the effects of radiation. We can also look at, when we think about future space missions, we know that it's going to take a while to get to Mars, and it's going to take some time to get farther. So the International Space Station has given us an opportunity to see what happens when humans are in a space environment or in a microgravity environment where they're in free fall for long periods of time. And this is really important, so we understand the effect of the lack of gravity on humans. We also understand what it's like to be confined in a small environment for long periods of time. And we're starting to understand just the kind of technology we need in order to create safe travel for humans, and also to address some of the challenges in robotic missions far from Earth.
The most recent addition to the ISS, a Russian segment with a European robotic arm, will help alleviate the stretched resources and capabilities of the station.
The ERA arm is completely symmetrical. This means it has a hand or an end effector at both sides, and that each side can serve as the tip as well as the shoulder. So it means that if you have multiple base points on the Russian segment, you can go from one base point to the other, then release your tip or your shoulder, which becomes tip, and then manipulate a payload. So in that sense, it has freedom of motion on the space station.
The robotic arm can be used for example, take payloads out of an airlock autonomously without the risk of an extravehicular activity, for example, and put equipment on the outside. It can be used for inspection. It can be used for putting big new modules, for example, and putting it on the space station, move big things around. And also it can be used to help the cosmonauts when they're doing a spacewalk, to move cosmonauts around or big payloads while the astronauts and cosmonauts have their hands free to work on the outside. So it can be used in several ways.
When we operate the ERA on the ISS, we're obviously going to learn a lot about how to use robots in space. How the robots work in space. We'll have feedback to our engineering process if we finally know what is the performance during its use in space. But we'll also learn on what we can best do with robots, what we can best do with people, and learn about the cooperation. And all of that is going to be very, very useful when we would go further into the universe and still have for sure robots initially, but maybe at some point in time also people with robots. So we're really looking forward to all what we can learn from the experience on the ISS with ERA.
Another addition to the station delivered by a SpaceX cargo module is a commercially funded Bishop airlock module. Operated by robotic arms, the commercial airlock allows easy transfer of payloads from within the station to outside for external deployment and to launch CubeSats, which is a burgeoning operational requirement. This will allow for more commercial payload throughput for industrial applications.
One issue that some European scientists worked on is that, first of all, we know that astronauts, after they've been in space for a long time, it's like their sense of taste changes a bit. And the longer they're up there, the more they crave spicier foods or saltier foods. So they start adding more salt to their meals. Well, one of the things that happens as they increase their salt ingestion is that it changes the pH of their blood. It makes it a little bit more acid, not a lot, but just a little bit. And so the body adapts to this acidity by trying to raise the pH just a little bit by providing calcium that comes from our bones. So they actually have increased dissolving of the bones to get that calcium to bring that pH up, but at the same time, we're also seeing that because they don't use their bones very much, because in a microgravity environment, you don't have to fight gravity to stand up straight, that they're already experiencing some bone loss. So we're starting to see that because of this, we're starting to see that this change of taste results in an increase in salt consumption that can actually speed the bone loss in space. So here we're seeing two different effects, and we know here on Earth, we now know that perhaps the increased salt consumption isn't just a cardiovascular effect, but it could have perhaps contribute to bone loss and osteoporosis in humans here on Earth. And we didn't really see that effect until we went to space. The International Space Station provides a platform that we have humans that can act as subjects, but also operators of science. And it's also the only platform that we've had where scientists have the opportunity to do an experiment, see the results, and come back and prepare another experiment. And if something doesn't work, or if they have a second opportunity. And unfortunately, we don't see that with other missions.
What is next? We have now just a bit more than 20 years of ISS operation, very successful, and really incredible science and experiments that have been conducted, and we still learn every single day new things there, and this is really good. So what's next? What will happen is, for sure, that by the end of this decade, we will have commercial space stations up there. There are about 4 projects in the planning today in the US. And the question is, does Europe participate there? Does Europe have its own independent solution? And this is a big question that we need to address. But yes, the space station as we know it today, at the end of this decade, will not exist anymore and will be replaced by some commercial stations. And this is a big change. And Europe needs to be active and show leadership in making this change and really be part of it in this next era, which will come at the end of this decade.
2 commercial projects are well underway to develop commercial stations for industry and tourism. Axiom Space are developing their station to be assembled in 4 modules whilst attached to the ISS. The 4th module will allow the station to deploy its own solar panels and become independent from the ISS. Eventually, Axiom Station will detach and orbit independently from the ISS.
Hi, I'm Gerard Valle, and I'm the Structures, Mechanisms, and Soft Good Lead for Sierra Space Life Habitat. We're really just testing the structural restraint layer, which is what carries the load, and it's 1/3 the size of a life habitat.
So the restraint layer is made up of a material called Vectran. Vectran is an extremely high-strength material, performs really well in this application. It gets us the best performance while maximizing the livable volume inside the habitat.
Pretty amazing.
Sierra Space has been successful in developing their inflatable modules and are also developing their own spacecraft, the Dream Chaser, to service the station called Orbital Reef. First developed in test flight as a crewed reusable space plane in 2013, the Dream Chaser was not selected by NASA in their commercial crew program. However, Sierra Space persisted with an unmanned cargo version and have built 3 so far. The design of the lifting body was derived from an earlier cancelled NASA project HL-20 spaceplane, a concept from earlier lifting body designs like the X-24 and HL-10. To be launched conventionally on a Vulcan Centaur or Ariane space rocket, and to fly back to Earth and land on a runway like the Space Shuttle. The craft will be powered with a vortex engine burning propane and nitrous oxide. It will be able to carry 5,000 kilograms of payload to the orbital reef, and eventually a crewed version will be capable of delivering between 3 to 7 crew or paying tourists. One growing problem, yet to be resolved for these new stations and other orbital assets, is space debris.
At the moment, the most known encounters are between active satellites and space debris. An example of such an event happened in 2009, where we had a collision between an active telecommunications satellite, Iridium, with an inactive space debris satellite, Cosmos. So this collision actually resulted in thousands of fragments, and many of them are still in orbit.
The danger of space junk destroying operational satellites and even manned spacecraft is a growing concern.
Space debris is the result of our activities in space. So we have no longer functioning satellites, and we have spent upper stages and the fragments. And in total, we know of about 28,000 objects that we can track, that means follow up from ground. We know of 900,000 objects that are larger than a centimeter. And we know of about 128 million of objects larger than a millimeter. And that shows that the largest contribution in numbers are these small fragments. And unfortunately, collisions and explosions are forecast to continue in space, and that means the population will still grow.
We are launching more and more. In the past, it was only the big space nations, let me call it that way, that were launching. By now, space has been opened up to commercial activities, and therefore we see more and more satellites being launched. Is this an issue for space debris? I would like to say no, if people behave properly. So if we really manage in a proper way the end of life of the satellite, it's not going to be an issue. The point is, will we manage those satellites in a proper way, yes or no? And we see that there is a tendency still to disregard what do I do with my satellite once it reaches end of life, and not consider it since the very beginning. Situation has improved a lot in the past 10 years, but we still have to do some teaching on how important it is to be considered since the very beginning of the design of a project.
Several concepts are in play to remove this orbital debris. For the larger objects, capturing them with spacecraft with arms or grapples, then performing a deorbit burn, dragging the debris down to burn up in the atmosphere. There is another resource available in orbit: sunlight. Why not capture it with solar sails and beam the electricity down to Earth? Massive solar farms comprising of many small mass-produced solar satellites launched into orbit on low-cost reusable rockets. Assembled together in orbit using advanced robotic techniques, and once completed, these satellites will collect the full power of the sun's energy 24 hours a day, 7 days a week, and beam it wirelessly down to Earth to receiver stations, which will turn it back into electricity and deliver it to the grid. Space-based solar power, continuously available, inexhaustible, and sustainable. A scalable energy source that could help meet the world's clean energy goals.